I should be online. Let me quickly make sure that everything is working. Right, looks like we're live. Let me double check audio is coming through. Alright, and it looks like we are ready to go. Yeah, I'll just get straight into it, because this is a topic I actually don't remember that well, so I'll probably be doing a lot more trivial things than I normally do. So, anyways. Chapter 19, Lattices and Boolean Algebras. The axioms of a ring give structure to the operations of addition and multiplication on a set. However, we can construct algebraic structures, known as lattices and Boolean algebras, that generalize other types of operations. For example, the important operations on sets are inclusion, union, and intersection. Lattices are generalizations of order relations on algebraic spaces, such as set inclusion in set theory and inequality in the familiar number systems n, z, q, and r. Boolean algebras generalize the operations of intersection and union. Lattices and Boolean algebras have found application in logic, circuit theory, and probability. So, section 19.1, Lattices. We begin the study of lattices and Boolean algebras by generalizing the idea of inequality. Recall that a relation on a set X is a subset of the Cartesian product of X with itself. A relation P on X is called a partial order of X if it satisfies the following axioms. So the relation is reflexive. So calling the relation R something like less than or equal to, we have A is less than or equal to B. The relation is antisymmetric. So if A is less than or equal to B, and B is less than or equal to A, then A is equal to B, and it's transitive. So A is less than or equal to B, and B is less than or equal to C, implies that A is less than or equal to C. The notation they use here is if AB is in P and BA is in P, which is the same thing in this case as saying AB is the same as saying A is less than or equal to P. It's a similar thing to when we were describing field of fractions previously, that the ordered pair, we just write it as an ordered pair information-wise. You think of it in terms of being in a different notation, the less than or equal to notation. We will usually write A is less than or equal to B to mean A, B is in P, unless some other symbol is naturally associated with a particular partial order, such as A is less than or equal to B with the integers A and B, or A is a subset of B with sets A and B. A set X together with a partial order less than or equal to is called a partially ordered set, or poset. Example 19.1. The set of integers, or rationals or reals, is a poset, where A is less than or equal to B has the usual meaning for two integers A and B in the integers. Example 19.2. Let X be any set. We will define the power set of X to be the set of all subsets of X. We denote the power set of X by P of X. For example, let X be equal to the three element set ABC. Then P of X is the set of all subsets of the set ABC. So, the empty set, the set including A, set including B, set including C, set including AB, set including AC, set including BC, and set including ABC. On any power set of X, set inclusion subset, what we call the set inclusion, the inclusions of subset, is a partial order. We can represent the order on ABC schematically by a diagram such as the figure in 19.3. So this is saying that A is a superset of the empty set, B is a superset of the empty set, and we have the relations where if we have a line going up, then the element at the beginning of a line is the subset of the line of the element at the end of the line. Which is why, for example, we don't have a line between B and AC here, because B is not a subset of AC, so there won't be a line. So this is the partial order on PABC. Example 19.4. Let G be a group. Then the set of subgroups of G is a poset, where the partial order is set inclusion. Example 19.5. There can be more than one partial order on a particular set. We can form a partial order on N by A is less than or equal to B, if A divides B. The relation is certainly reflexive, since A divides A for all A and N. If M divides N and N divides M, then M is equal to N. Hence, the relation is also antisymmetric. The relation is transitive, because if M divides N and N divides P, then M divides P. Example 19.6. Let x be equal to 1, 2, 3, 4, 6, 8, 12, 24. Be the set of divisors of 24 with a partial order defined in example 19.5. So the division partial order. We have a figure, the partial order is shown. 1 divides 2, 2 divides 6 and 4. 3 does not divide 4, so there's not a line there, and then it respectively goes up. Let y be a subset of a poset x. So commonly, when we have a poset, we'll define the poset as being this. Or wait, yeah, use this notation. So let y be a subset of x. An element in u is in x is an upper bound of y if a is less than or equal to u for every y, a and y. So if for all a in y, we have that a is less than or equal to u is a upper bound for y. If u is an upper bound of y such that u is less than or equal to v for every other upper bound v of y, then u is called a least upper bound or a supremum of y. So in this case, this is a supremum if given any other upper bound v, we have that u is less than or equal to v. Implies u is supremum of y. And then similarly, an element L in X is said to be a lower bound if L is less than or equal to A for all A and Y, and if L is the lowest lower bound of Y, such that K is greater than or equal to L for every other lower bound K of Y, then L is called a greatest lower bound, or infimum of Y. So example 19.8. Let y be equal to 2, 3, 4, 6 be contained in the set X of example 19.6, the division example. Then y has upper bounds 12 and 24, with 12 a least upper bound. The only lower bound is 1, hence it must be a greatest lower bound. As it turns out, least upper bounds and greatest lower bounds are unique if they exist. So, theorem 19.9, let y be a non-empty subset of a poset X. If, this is important to note here, if y has a least upper bound, then y has a unique least upper bound. And similarly, if y has a greatest lower bound, then y has a unique lower bound. So proof. Let u1 and u2 be least upper bounds for y. By the definition of the least upper bound, u1 is less than or equal to u for all upper bounds u of y. So in particular, u1 is less than or equal to u2. Then, similarly, we have u2 is less than or equal to u1 by the same logic, and therefore by anti-symmetry we have u1 is equal to u2. A similar argument can show that the greatest lower bound is unique. Now, on many posets, it is possible to define binary operations by using the greatest lower bound and the least upper bound of two elements. A lattice is a poset L, such that every pair of elements in L has a least upper bound and a greatest lower bound. The least upper bound of AB is called the join of AB, and is denoted by A wedge B, and the greatest lower bound of A, B, and L is called a meet of A and B, and is denoted A intersected with B. Okay, let me write this out. So a lattice is a poset such that for all A, B, and L, supremum of the set A, B is equal to A union with B, A or B, and infimum of A, B equals A and B, strict and, exist. This is also called, I'll note this here because I'm not used to this terminology. We have, this is called the join, this is called the meet. And there will be no justification for this terminology set theoretic wise, which I imagine it will give. So, example 19.10. Let X be a set. Then the power set of X, P of x is a lattice. For true sets A and B in P of x, the least upper bound of A and B is A union B. Certainly, A union B is an upper bound of A and B, since A is a subset of A union B and B is a subset of A union B. If C is some other set containing both A and B, then C must contain A union B. Hence, A union B is the least upper bound of A and B. Similarly, the greatest lower bound of A and B is A cap B. So you can think of this as like joining the elements of A and B, which is why we call it join, and this is meeting the elements of A and B, which is why we call it the meet. Example 19.11. Let G be a group, and suppose that X is a set of subgroups of G. Then X is a poset ordered by set theoretic inclusion, subset. The set of subgroups of G is also a lattice. If H and K are subgroups of G, the greatest lower bound of H and K is H cap K. The set H union K may not be a subgroup of G, but we leave it as an exercise to show that the least upper bound of H and K is the subgroup generated by H union K. In set theory, we have certain duality conditions. For example, by De Morgan's laws, any statement about sets that is true about A union B prime must also be true about A union B complement must also be true about A complement cap B complement. We also have a duality principle for lattices. Oh gosh, the axiom of duality. Any statement that is true for all lattices remains true when less than or equal to is replaced than greater than or equal to, and join and meet are interchanged throughout the statement. So what this is basically saying is that, yeah, I understand why they do this. Basically, if you're working set theoretically, you are able to just replace the statements by because of equivalent conditions. For now, yeah, it does have to just be taken as an axiom for now. The following theorem tells us that a lattice is an algebraic structure with two binary operations that satisfy certain axioms. So, yeah. Also, I'll just reiterate one more time because this is like slightly weirdly phrased. This axiom, this principle of duality, is basically a proof-saving measure. You can prove completely abstract set theoretically that this statement is true, but it's also just kind of intuitive from the definition. Gosh, I don't know how to properly explain it. It's one of those things where it's kind of like opposite categories. You can work completely in opposite categories to prove everything, but as long as someone has done the foundational work, we're just taking this as principle so that we only have to do half the work. Because you can show everything is true, but because the infimum is for example, to find dual to the supremum, why do all that extra work? We already have all that there. Slightly unsatisfying personally, but is what it is. So, theorem 19.13. If L is a lattice, then the binary operations meet and join satisfy the following properties for A, B, C, and L. 1. The commutativity laws. A join B is equal to B join A, and A meet B is equal to B meet A. The associative laws. A join B join C is equal to A join B join C, and A meet B meet C is equal to A meet B meet C. The idempotent laws. A join A is equal to A, and A meet A is equal to A. And the absorption laws. A joined A meet B is equal to A, and A meet A join B is equal to A. So as we notice, in each of these statements we have a dual expression, and because we're talking about equality here, we're talking about a less than or equal to statement, a less than and a greater than statement all in one. So we use the principle of duality to basically say, okay, we only need to prove this for one of these cases, because the other is just handled by this axiomatic principle of duality. So, proof. By the principle of duality, we need only prove the first statement in each part. 1. By definition, A join B is the least upper bound of A and B join A is the least upper bound of BA. However, the sets AB and BA are equal. 2. We will show that A join B join C and A join B join C are both least upper bounds of A, B, C. Let D be A joined B. Then C is less than or equal to D join C is equal to A join B join C. We also have that A is less than or equal to A join B is equal to D is less than or equal to G join C is equal to A join B join C. A similar argument demonstrates that B is less than or equal to A join B join C. Therefore, A join B join C is an upper bound of ABC. We now need to show that A join B join C is the least upper bound of ABC. Let U be some other upper bound of ABC. Then A is less than or equal to U, and B is less than or equal to U. Hence, D is equal to A join B is less than or equal to U. Since C is less than or equal to U, it follows that A join B join C is equal to D join C is less than or equal to U. Therefore, A join B join C must be the least upper bound of ABC. The argument that shows that A join B join C is the least upper bound of ABC is the exact same with the simple reindexing of the terms to the associativity property, and also using the previous commutativity property. Consequently, A joined B join C is equal to A join B join C. 3. The join of A and A is the least upper bound of A. Hence, A joined A is equal to A. 4. Let D equal A join B. Then A is less than or equal to A join D. On the other hand, D is equal to A meet B is less than or equal to A, and so A joined D is less than or equal to A. Therefore, A joined A meet B is equal to A. Okay. Given any arbitrary set L with operations join and meet, satisfying the conditions of the previous theorem, it is natural to ask whether or not this set comes from some lattice. The following theorem says that this is always the case. So, Theorem 19.14. Let L be a non-empty set with two binary operations, join and meet, satisfying the commutative, associative, idempotent, and absorption laws. We can define a partial order on L by A is less than or equal to B if A join B is equal to B. Therefore, L is a lattice with respect to less than or equal if for all A, B, and L, we define the least upper bound and greatest lower bound of A and B by A join B and A meet B respectively. So proof. We first show that L is a poset under this new operation less than or equal to. Since A join A is equal to A is less than or equal to A, and less than or equal to is reflexive. To show that less than or is equal to is antisymmetric, let A less than or equal to B and B less than or equal to A. Then A join B is equal to B, and B join A is equal to A. By the commutative law, B is equal to A join B is equal to B join A is equal to A. Finally, we must show that A is less than or equal to is transitive. Let A less than or equal to B, and B less than or equal to C. Then A join B equals B, and B join C is equal to C. Thus, A join C is equal to A join B join C is equal to A join B join C is equal to B join C is equal to C, or A is less than or equal to C. To then now show that L is a lattice, we must prove that A join B and A meet B are, respectively, the least upper and greatest lower bounds of A and B. Since A is equal to A join B meet A, and A is equal to A meet Since A is equal to A join B meet A, and A is equal to A meet B, A meet A join B, it follows that A is less than or equal to A join B. Similarly, B is less than or equal to A join B. Therefore, A join B is an upper bound for A and B. Let U be any other upper bound of A and B. Then A is less than or equal to U and B is less than or equal to U. But A join B is less than or equal to U, since A join B join U is equal to A join B join U is equal to A join U is equal to U. The proof that A meet B is the greatest lower bound of A and B is left as an exercise. Oh my gosh, okay. Boolean Algebras. Let us investigate the example of power set Px of a set more closely. The power set in a lattice is The power set is a lattice that is ordered by inclusion. By the definition of the power set, the largest element in Px is X itself, and the smallest element is the empty set. The empty set. For any set A in P of X, we know that A intersected with X is equal to A, and A union the empty set is equal to A. This is just the following definition of lattices. An element I in a poset X is the largest element if A is less than or equal to I for all A in X. An element O is the smallest element of X if O is less than or equal to A for all A in X. Let A be in P of X. Recall that the complement of A is A prime is equal to X over A is equal to X such that X is an X and X is not an A. We know that A joined A prime is equal to X and A intersected A prime is equal to the empty set. We can generalize this example for lattices. A lattice L with the largest element I and the smallest element O is complemented if for each A and L there exists an A prime such that A join A prime is equal to I and A meet A prime is equal to 0. In a lattice L, the binary operations join and meet must satisfy commutativity and associativity laws. However, they need not satisfy the distributive law. A meet B join C is equal to A meet B join A meet C. However, in P of X, the distributive law is satisfied, since A intersected with B union C is equal to A intersected with B union A intersected with C, for A, B, and C in P of X. We say that a lattice L is distributive if the following law holds. So A join B, A meet B join C is equal to A meet B join A meet C for all A, B, and C in L. Now, a lattice L is distributive if and only if A meet B join C is equal to A join B meet A join C for all A, B, and C in L. So, this is basically saying that we're able to flip all of the terms in this part to show that the law holds basically in axiomatic duality. So let us assume that L is a distributive lattice. A join B meet C is equal to A join A meet C join B meet C. Oh, oh my bad. Okay. A join A meet C join B meet C is equal to A join C meets A join C meets B equals A join C meets A join B is equal to A join B meets C is equal to A join B meet A join A meet B join meet C is equal to A join B meet A join C, which is basically just a bunch of reindexing and using both distributive and associative and commutative everywhere. The converse follows immediately from the duality principle. A Boolean algebra B is a lattice B with greatest element I and smallest element O, such that B is both distributive and complemented. So, let's write this. Alright, so it's a Boolean algebra. L is a Boolean algebra. Let me make sure I have all the definitions correct. Largest element. So we want an element I such that A is less than or equal to I. We want an element O such that O is less than or equal to A. And we want there for every A to exist some A prime such that A join A prime is equal to I. And A meet A prime is equal to O. That satisfies the distributive law. Or that A join B meet C is equal to A meet C join B meet C. Oh man, okay. By associativity, yeah, this is actually a fine definition. Just a bit weird in how I read it out. Alright, the power set of X, P of X, is our prototype for a Boolean algebra. As it turns out, it is also one of the most important Boolean algebras. The following theorem allows us to characterize Boolean algebras in terms of the binary relations join and meet without mention of the fact that a Boolean algebra is a poset. So, theorem 19.16. A set B is a Boolean algebra if and only if there exist binary operations join and meet on B satisfying the following axioms: commutativity, associativity, distributivity, having a smallest and largest element, and complementivity. So we don't even need the poset in this, we just need that these operations hold. So proof. Let B be a set satisfying 1 to 5 in the theorem. One of the idempotent laws is satisfied, since A is equal to A join 0 is equal to A join A meet A prime is equal to A join A meet A join A prime is equal to A join A meet I is equal to A join A. Observe that I join B is equal to B meet B join B prime join B is equal to 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 I. Consequently, the first of the two absorption laws hold, since A join A meet B is equal to A meet I join A meet B is equal to A meet I join B is equal to A meet I is equal to A. The other idempotent and absorption laws are proven similarly. Since B also satisfies 1 to 3, the condition of theorems 19.14 are met. Therefore, B must be a lattice. Let me make sure I'm not failing something here. Okay. For A and B, O join A is equal to A. Hence, O is less than or equal to A, and O is the smallest element in B. To show that I is the largest element in B, we will first show that A join B equals B is equivalent to A meet B is equal to A. Since A join I is equal to I for all A and B, using the absorption laws, we can determine that A join I is equal to A join I meet I. A meet I join I is equal to I join I meet A is equal to I. Or, A is less than or equal to I for all A and B. Finally, since we know that B is complemented by 5, B must be Boolean algebra. Conversely, suppose that B is a Boolean algebra. Let I and O be the greatest and least elements respectively. If we define A join B and A meet B as the least and greatest lower bound, the least upper and greatest lower bounds of AB, then B is a Boolean algebra by theorem 19.14, theorem 19.15, and our hypothesis. Okay. Many other identities hold in the Boolean algebra. Alright, before I worry about them, let me make sure I also have the idempotent laws written down. Considering I don't think I did, and that's kind of a mistake. So yeah, commutative, associative, idempotent, absorption. Okay. So theorem 19.17, let B be an Boolean algebra. Then A meet I is equal to I, and A join I is equal to I, and A meet B O is equal to O for all A and B. If A join B is equal to A join C, and B meet B is equal to A meet C for A, B, and C and B, then B is equal to C. If A join B is equal to I, and A meet B is equal to O, then B is equal to A prime. If A prime prime, we have A prime prime is equal to A for all A and B. We have that I prime is equal to O, and O is equal to I prime, O prime is equal to I. And A join B prime is equal to A prime meet B prime, and A meet B prime is equal to A prime meet B prime, or De Morgan's laws. So, we will only prove 2. The rest of the identities are left as exercises. Oh, how fun. For A join B is equal to A join C, and A meet B is equal to A meet C, we have that B is equal to B join B meet A by absorption, then A join A meet B by commutativity, then B join A meet C by replacement, then A join A meet B join C by distributivity, then by commutativity we have A join B meet B join C, then by replacement is equal to A join C meet B join C, and then equals by commutativity C join A meet C join B is equal to reversing the distributivity is equal to C meet A meet B, or C join A meet B is equal to C join A meet C is equal to C join C meet A is equal to, by absorption one last time, C. Okay. Finite Boolean algebras. A Boolean algebra is a finite Boolean algebra if it contains a number of elements if it contains a finite number of elements as a set. So basically, the cardinality of L as our lattice is like not infinity. Finite Boolean algebras are particularly nice since we can classify them up to isomorphism. Ooh, category theory on this. Let B and C be Boolean algebras. A bijective map phi from B to C is an isomorphism of Boolean algebras if phi of A join B is equal to phi of A join phi of B, and phi of A meet B is equal to phi of A meet phi of B, for all A and B and B. We will show that any finite Boolean algebra is isomorphic to the Boolean algebra obtained by taking the power set of some finite set X. We will need a few lemmas and definitions before we prove this result. Let B be a finite Boolean algebra. An element A in B is an atom of B if A is not equal to 0, and A meet B is equal to A for all B and B with B not equal to O. Equivalently, A is an atom of B if there is no B in B with B not equal to O, distinct from A, such that O is less than or equal to B is less than or equal to A. So I'll quick put that, like shrink this whiteboard part of it, and then we have an atom being some A in L such that O is less than, or there's I can just put this implies B equals to A or B equals to O. So lemma 19.18. Let B be a finite Boolean algebra. If B is an element of B with B not equal to O, then there is an atom A in B such that A is less than or equal to B. So proof. If B is an atom, we let A equal B. Otherwise, choose an element B1 not equal to O or B such that B1 is less than or equal to B. We are guaranteed that this is possible since B is not an atom. If B1 is an atom, then we are done. If not, choose B2 not equal to O or B1 such that B2 is less than or equal to B1. Again, if B2 is an atom, let A equals B2. Continuing this process, we obtain a chain 0 less than B less than or equal to B1 less than or equal to B2 all the way on to greater than or equal to A. Since B is a finite Boolean algebra, this chain must be finite. That is, for some k, Bk is an atom. Simply let A equals Bk and we're done. Lemma 19.19. Let A and B be atoms in a finite Boolean algebra B such that A is not equal to B. Then, A meet B is equal to O. Proof. Since A meet B is the greatest lower bound of A and B, we know that A less than or equal to A meet B is less than or equal to A. Hence, either A meet B is equal to A, or A meet B is equal to O. However, if A meet B is equal to A, then either A is less than or equal to B, or A is equal to O. In either case, we have a contradiction, because A and B are both atoms. Therefore, A join B is equal to O. Lemma 19.20. Let B be a Boolean algebra, and A, B be an elements in B. The following statements are equivalent. First, A is less than or equal to B. Second, A join B complement is equal to O. And 3, A complement join B is equal to I. Proof. First, proving that this implies this. If A is less than or equal to B, then A join B is equal to B. Therefore, A in meet B prime is equal to A meet A join B prime is equal to A meet A prime join B prime is equal to A meet A prime join B prime is equal to O meet B prime is equal to O. 2 implies 3. If A join B prime is equal to O, then A prime join B is equal to A meet B prime prime is equal to O prime is equal to I. And then finally 3 implies 1. If A prime join B is equal to I, then A is equal to A meet B A prime join B is equal to A join A prime. A meet A prime join A meet B is equal to O join A meet B is equal to A meet B. And thus, A is less than or equal to B by the definition of the infimum. Lemma 19.21. Let B be a Boolean algebra and B and C be elements in B such that B is not less than or equal to C. Then there exists an atom A and B such that A is less than or equal to B and A is not less than or equal to C. Proof. By lemma 19.20, B meets C prime is not equal to O. Hence, there exists an atom A such that A is less than or equal to B meets C prime. Consequently, A is less than or equal to B, and A is not less than or equal to C prime. Lemma 19.22. Let B be in B, and A1 all the way to AN be the atoms of B such that A1 is less than or equal to B. Then B is equal to A1 join A1 join A2 join all the way up to join AN. Furthermore, if A1 all the way to AN are atoms of B such that A1 is A is less than or equal to B, AI is less than or equal to B, and B is equal to A join A1 join all the way to join AN, then A equals A sub I for some I equals 1 to N. Proof. Let B1 equals A1 join all the way on to join A sub N. Since A sub I is less than or equal to B for each I, we know that B sub 1 is less than or equal to B. If we can show that B is less than or equal to B sub 1, then the lemma is true by antisymmetry. Assume B is less than or equal is not less than or equal to B1, then there exists an atom A such that A is less than or equal to B, and A is not less than or equal to B1. Since A is an atom, and A is less than or equal to B, we can deduce that A equals A sub I for some A sub I. However, this is impossible, since A is less than or equal to B sub 1. Therefore, B is less than or equal to B sub 1. Whew, a nice argument, but a lot. Now suppose that B is equal to A sub 1 join all the way to join A sub N. If A is an atom less than B, A is equal to A meet B is equal to A meet A1 join all the way to join A sub N is equal to, you actually prove this identity by induction, A meet A1 join all the way to join A meet A sub N. But each term is either O or A with A meet AI occurring for only one AI. Hence, by lemma 19.19, A is equal to A sub I for some I. Theorem 19.23. Let B be a finite Boolean algebra. Then there exists a set X such that B is isomorphic to P of X. Proof. We will show that B is isomorphic to P of X, where X is a set of atoms of B. Let A be in B. By lemma 19.22, we can write a uniquely as a equals a1 join all the way to join a sub n for a sub 1 to a sub n in x. Consequently, we define a map phi from b to p of x by phi of a is equal to phi of a1 joined all the way to join a sub n is equal to the set a sub 1 all the way to a sub n. Clearly, we have that phi is onto. Now, let a be equal to a1 join all the way to join a sub n, and b is equal to b sub 1 join all the way to b sub m be elements in B, where each a sub I and each b sub I is an atom. If phi of a is equal to phi of b, then a1 all the way to an is equal to b1 all the way to bm, and a is equal to b. Consequently, phi is injective. The join of a and b is preserved by phi, since phi of a join b is equal to phi of a1 join all the way to join an, join b1 join all the way to bn is equal to a1 all the way to an, b1 all the way to bm as sets. Then the set a1 to an union b1 all the way to bm is equal to phi of a1 joined all the way to an join union phi of b1 join all the way to bm. Okay, that's a random typo. Okay, that should not be me. That's very wrong. Yeah, weird typo. Anyways, is equal to phi of a union phi of b. Similarly, phi of a meets b is equal to phi of a intersected with phi of b. We leave the proof of the following corollary as an exercise. Corollary 19.24. The order of any finite Boolean algebra must be 2 to the n for some positive integer n. I'll probably do this exercise, but if you know much about like power sets and why they must have order 2 to the cardinality of whatever you have, and we have a power set on the set of atoms, it kind of just really naturally follows. So the algebra of electrical circuits. Ooh, this is an application I actually know like shamefully little about, so I'm excited for this. The usefulness of Boolean algebras has become increasingly apparent over the past several decades with the development of the modern computer. The circuit design of computer chips can be expressed in terms of Boolean algebras. In this section, we will develop the Boolean algebra of electrical circuits and switches. However, these results can easily be generalized to the design of integrated computer circuitry. A switch is a device, located at some point in an electrical circuit, that controls the flow of current through the circuit. Each switch has 2 possible states. It can be open, and not allow the passage of the current through the circuit, or it can be closed, and allow the passage of the current. So, I'm just going to put this here. I assume, just for completeness, I should probably put diagrams. So, we have some, like, electrical circuit here, with this being our power source, and then we have this, like, circuit here. This is not standard notation, but basically this right here is a switch. And what this switch is it's in one of 2 states. This, call it state 1, is open. Notice that if this state is open, this gate actually, this passage doesn't exist. So current will flow onto here, and then it will stop. It won't be able to complete the loop. Now, if we are in, let's call it state 2, and we have that this is actually closed, or this is closed, then it will allow a full completion of current through the loop, and it will give us an electrical current. Alright, these states are mutually exclusive. We require that every switch be in one state or the other. A switch cannot be open and closed at the same time. Also, if one switch is always in the same state as another, we will denote both by the same letter. That is, 2 switches that are both labeled with the same letter A will always be open at the same time and closed at the same time. So basically, if we have this switch here and also this switch here, don't mind the fact that it's cutting through, we call this switch A, this switch also A. If this is the case, then if this is open, and if this is closed, and vice versa. But that image looks disgusting, so fix that, yeah. Given 2 switches, we can construct 2 fundamental types of circuits. The 2 switches A and B are to be in series if they make up a circuit of type A that is illustrated in 19.25. So it is in series if we have our battery source or our power source, and it is a straight line through. So this is a series, and they are in parallel if they actually branch off at this point into two separate paths to complete the circuit. Let me make sure I spell parallel. P-A-R-A. Para. Two L's and parallel. Oh my gosh. I'm not going to embarrass myself. For my friends who had me during AP Physics C, I will not make a spelling blunder like the one I made on the whiteboard that fateful day, if you know what I'm talking about. That was embarrassing. How do you spell both parallel and circuit wrong when you're talking about parallel circuits? Anyways. If they form a circuit that appears in figure 19.26. In the case of a parallel circuit, current can pass between A and B if either one of the switches is closed. We denote the parallel combination of circuits A and B by A join B. So if we have switches like A and B, right? Then we have them in series. Like, let's say this section is a switch. This is A, this is B. And then if we have switches, actually that makes sense. Then we have switches A and B here, and this is denoted, this whole circuit, the series circuit is denoted by A meet B. So this is denoted by A meet B, and this is denoted by A join B. And one way to think of it is that since this is the infimum, we must have both circuits closed in order for current to pass through. Like, if one of these is closed, you can think of one of these as being the empty set. And this is intersection, so like no current will go. While if at least one of these is open, you can think of this as union. Alright, we can build more complicated electrical circuits out of parallel and series and parallel circuits by replacing any switch in the current with one of these two fundamental types of circuits. Circuits constructed in this manner are called series parallel circuits. We will consider two circuits equivalent if they act the same. That is, if we set the switches in equivalent circuits exactly the same way we will obtain the same result. For example, in a series circuit, A join B is exactly the same as B join A. Notice that this is exactly the commutative law for Boolean algebras. In fact, the set of all non-series parallel circuits forms a Boolean algebra under the operations of join and meet. Okay, this is kind of wild. I'm actually really enjoying this. We can use diagrams to verify the different axioms of a Boolean algebra. The distributive law, A meet B join C is equal to A meet B join A meet C, is illustrated in figure 19.27. So over on the left side, we have this. Oh, that's so cool. Oh, it's such a cool representation of it. Oh my gosh. A join B meets C. We have A in series. A and this circuit are in series, and then this circuit's in parallel. Where for this, we have two circuits in parallel, but each individually are in series. A circuit that is always closed in I is in our algebra. A circuit that is always open is O. The laws for A join A prime is equal to O, and A meet A prime equal to I are shown in figure 19.28. So A joined, basically we can think of A prime as if this switch is open, A prime is closed. And if A prime is closed, if A prime is open, then A is closed. So saying this is that one of these circuits will always be closed, so it's always like no current. And one of these circuits will always be open, so it is some current. Alright, example 19.29. Every Boolean expression representing a switching circuit. For example, given the expressions A join B, meet A join B prime, meet A join B, we can construct the figure in 19.32, which is this figure right here. Theorem 19.30. Oh, this is so cool. Theorem 19.30. The set of all circuits is a Boolean algebra. We leave as exercise the proof of this theorem for the Boolean algebra axioms, not yet verified. We can now apply the techniques of Boolean algebras to switching theory. Example 19.31. Given a complex circuit, we can now apply the techniques of Boolean algebra to reduce it to a simpler one. Consider the circuit in figure 19.32, this kind of mess right here. Since A join B meet A join B prime, meet A join B is equal to A join B meet A join B meet A join B prime is equal to A join B meet A join B prime is equal to A join B prime is equal to A join O is equal to A. We can replace the more complicated circuit with a circuit containing a single switch and achieves the same function. So this reduction gives us a way to at least begin computing by hand, and especially in computer code, the most efficient circuits in terms of like switches. Like if we want to produce the minimum number of switches, what is the minimum number of operations like in order to actually minimum number of switches needed to have the logical operations that we want? Oh god. Alright, sage now. Historical note. George Boole was the first person to study lattices. In 1847, he published The Investigation of the Laws of Thought, a book in which he used lattices to formalize logic and the calculus of propositions. Boole believed that mathematics was a study of form rather than of content. That is, he was not so much concerned with what he was calculating as with how he was calculating it. Boole's work was carried on by his friend Augustus de Morgan. De Morgan observed the principle of duality often held in set theory, as is illustrated by De Morgan's laws for set theory. He believed, as did Boole, that mathematics was the study of symbols and abstract operations. Set theory and logic were further advanced by such mathematicians as Alfred North Whitehead, Bertrand Russell, and David Hilbert. In Principia Mathematica, Whitehead and Russell attempted to show the connection between mathematics and logic by the deduction of the natural number system from the rules of formal logic. If the natural numbers could be determined from logic itself, then so could much of the rest of existing mathematics. Hilbert attempted to build mathematics by using symbolic logic in a way that would prove the consistency of mathematics. His approach was dealt a mortal blow by Kurt Gödel, who proved that there will always be undecidable problems in any sufficiently rich axiomatic system. That is, that in any mathematical system of any consequence, there will always be statements that can never be proven either true or false. As often occurs, the basic research in pure mathematics later becomes indispensable in a wide variety of applications. Boolean algebras and logic have become essential in the design of the large-scale integrated circuitry found on today's computer chips. Sociologists have used lattices and Boolean algebras to model social hierarchies. Biologists have used them to describe biosystems. That's actually kind of wild. Don't know how I feel about that, because I don't know about the rigor of that, especially applying lattices to social hierarchies, but like that actually seems like an interesting model to make some hypotheses to test off of. Just always gotta be careful with however you run a model in a sociological environment. Alright, 19.4, reading questions. Describe succinctly what a poset is. Do not just list the defining properties, but give a description that another student of algebra who has never seen a poset might understand. For example, part of your answer might include what type of common algebraic topic a poset generalizes, and your answer should be short on symbols. It's a generalization of less than or equal to, which has equality built in, has the transitivity, A less than B less than C implies A less than C built in, and the anti-symmetry, which says that we can't have two objects that are not the same both be less than or equal to each other. Alright, how does a lattice differ from a poset? A lattice is in the spirit of the previous question, a lattice allows us to define the joint and lattices. What's a good intuitive description of lattices? I don't know if they're assuming like a set theoretic. They basically generalize union and intersection. We talk about the stuff that comprises both of the elements in something called a join, and we comprise the stuff that's in both of the elements in terms of meet. Alright, how does Boolean algebra differ from a lattice? Again, answer this in the spirit of the previous question. A Boolean algebra is basically a lattice with additional structure. Distributivity, the sense of complements, so that you're able to do like logic in terms of like if you have something, you have its complement in a set theoretic sense. Distributive, complement, the largest and smallest things. I think that's it. Yeah, I think that's it in terms of Boolean algebras. Oh gosh, I just keep forgetting all the exact properties. Give two perhaps related reasons why the discussion of finite Boolean algebras might center on the example of the power set of a finite set. So one is that every Boolean algebra is isomorphic to the Boolean algebra generated by the power set of a set. And second would be that the Boolean algebras, naturally, since they generalize on the ideas of intersection and unions, it's important to look at those examples to see what carries over to all of them. Describe a major innovation of the middle of the 20th century made possible by Boolean algebras. I guess it's talking about like simplification of circuits as a logical necessity or a logical thing, or like talking about like the modeling of certain behaviors where you have like infimums and supremums, just generally. Yeah, I think that should be it. And oh wait, not actually that many exercises. Huh, weird. So I guess before I jump into the exercises, you know what that means. All right, we are back, and we are ready to go. Okay, so I'll probably get rid of the series and parallel circuit stuff for now. I'm feeling like today, I might not do all the exercises because I want to like save time so that I can do chapter 20 later on. Because chapter 20, the next chapter is fairly short. It's actually way shorter than this chapter, and this chapter is short. So okay, So draw the lattice diagram for the power set of A, B, C, D with set inclusion relation, this. So we have, first of all, the empty set, A, B, C, D, A, B, A, C, A, D, A, B, C, B, D, C, D. Then we have A, B, C, A, B, D, A, C, D, B, C, D. Oh, that actually might be it for that. Then we have A, B, C, D. So then just drawing our normal diagram, called also a Hasse diagram, gives us this right here. I mean, this, okay, admittedly this does kind of look like a conspiracy board, but don't mind that. AD, let's have AD in this, we have BC in this, and this, we have BD in this, and this, and we have CD in this, and this, and then all these included up to here. This is our Hasse diagram for the 4-point set. Not exactly pretty. Not exactly pretty, but it is, it does work. So draw the diagram for the set of positive integer set divisor of 30. Is this posted a Boolean algebra? I guess we can do that. So 30, first of all, its prime factorizations are going to be equal to 2 times 3 times 5. So we have 1, then we have 2, 3, 5, then we have 6, 10, 15. Then we have from this, all we have is on from 30. So, oh wait, let me be careful about how I draw lines here. So it's this, 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 this. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have the cardinality for a Boolean algebra. Let's calculate, what does the A meet B in this? I assume A meet B is going to be the greatest common divisor of A, B. I'm going to assume A join B is equal to the least common multiple of A and B. Wait, I'm wondering. I'm pretty sure this is a Boolean algebra. Yes. Because we can think of this. Instead of thinking about this, we'll write out the prime factors of a number as a set. So we have 1, the set 1, the set 2, 3, 5, we have 2, 3, 2, 5, 3, 5. And then we have 2, 3, 5. So we can actually, that's fairly nice. So it looks like if the prime factorization of n has no repeated prime factors, then there's an isomorphism between the power set of, we can just consider this set also to be the empty set in this case. If n equals the product of pi has distinct prime factors, there's an isomorphism phi from n to the power set of the set p1, p2 all the way to pn. I wonder if you just have a lattice isomorphism. I'm wondering, okay, I'm gonna quick look up something. I don't know if it will be true. Or if it will be asked to prove. Okay. Okay, so something I want to try proving is, suppose we have a lattice homomorphism. We have a lattice homomorphism, L to B with B a Boolean algebra. Is L a Boolean algebra? I mean, I would think yes, because if you have a certain law in B, what you do is you apply that law using phi, and you apply the inverse isomorphism back to get the identity. Yeah. Yeah, nice. So if we can show, that means that we can show that, oh, that is possibly really cool. So that means that if we call least common multiple and greatest common divisor, by that kind of isomorphism I showed earlier, then that shows that we have, for example, uniqueness and such. Oh, that's really cool. Oh, that is really cool. That's a powerful general tool. Okay. Right, anyways. Draw a diagram of the lattice of subgroups of Z sub 12. Sure. So we have Z sub 12. As a subgroup, we have the subgroup, each subgroup of a cyclic group will be another cyclic group. Right. Or we'll divide the order. So we have Z sub 2, Z sub 3. We have E, Z sub 2, Z sub 3, Z sub 4, Z sub 6. Z sub 6. Yeah, because that's 2, and then we have a factorization of 2 times 2 times 3, which means there are 6 total elements. Also, this immediately shows it's very nice that this is not a Boolean algebra structure, so we have to examine group structures separately, which is funky. I like it. Yeah. So the lattice appears like so. Oh man, that is cool. That is cool. I wonder if you have a category of lattices as like a subset of, or subcategory of set with some additional structure. I wonder what category theoretic operations you have on that. Anyways. Let B be the set of positive integers that are divided to 210. give me a second to just I'm not cheating right now. Factorization of 210. Alright, the prime factorization of 210 is 2 times 3 times 5 times 7. Let me double check if that's actually right. That seems right, because it's 6 times 5 is 30 times 7 is equal to 210, yeah. So that means that we can just apply the isomorphism phi from 210 to the power set of 2, 3, 5, 7 to get an isomorphism, and then from there it shows that it's a Boolean algebra, because this is a Boolean algebra, and isomorphisms preserve the Boolean algebra. Or isomorphisms only take Boolean algebras to Boolean algebras. Proof or disproof. Z is a poset under the relation A less than B if A divides B. Oh, it just wants to show it's a poset. So A divides A. Oh wait, oh no, yeah, actually this is false. This is false. Because 1 divides -1 and -1 divides 1, but 1 is not equal to -1. What you could do is you could take one way to take it is that if you have a set such that A is less than or equal to A, and A less than or equal to B, and B less than or equal to C implies A is less than or equal to C, you can create this. If you only have this, you can create a new thing. Because what this is okay, how do I best describe this? This is a relation. We can define a relation lambda prime on the set of equivalence classes of A. What's an equivalence class of A? Or the equivalence classes, or some equivalence class. What's this equivalence class? We have A is equivalent to B if A is less than or equal to B, and B is less than or equal to A. It should be obvious that this actually induces, from just transitivity and reflexivity, this actually ensures some anti-symmetry. So what we actually have is that the division relation we have on the integers is actually the division on the natural numbers is the division relation almost the pseudo division relation on the the integers modulo this transformation. So I probably want to show it more formally. So define a pre-partial order. Define a pre-partial order to be some less than or equal to such that A is less than or equal to A, and A is less than or equal to B, B is less than or equal to C, implies that A is less than or equal to C. On a set, we call it a pre-partial by that, and we denote it as the set A with the pre-partial this. Now, we have a functor that takes pre-partial relations to partial relations. By first, we take the equivalence class. Actually, I think it would be a functor. It'd just be a really kind of wonky functor. So we have A prime. We have A prime be equal to A modulo the equivalence relation. With the equivalence relation given by A is similar to B if A is less than or equal to B and B is less than or equal to A. So now we define a equivalence relation on A prime. A prime less than by A is less than or equal to B. So we basically move from elements to equivalence classes. Now, to show it's well defined, because this is just a notion. It's always something you have to do with equivalence classes. You need to justify why it's well defined. Also, man, I have gone off the deep. I'm not even like doing the exercises anymore. I'm just kind of doing whatever. So to show that this is well defined, first of all, we want to show that if A is less than or equal to B, so basically, if A is less than or equal to B, with B is less than or equal to A, or actually I should put A prime here. A prime with B, and A prime less than or equal to A, with B less than or equal to B prime, with B prime less than or equal to A, or less than or equal to B. We want to show that actually at this point, you know, why am I even on this board if I'm doing like my own kind of freestyle thing? I might as well move to the full whiteboard. So working board, here we go. So we have this, bring this all over to this side on a pre-partial. By that, so we want to show if this is the case, then A is less than or equal to B implies that A prime is less than or equal to B prime. Or actually, and vice versa. So we have A prime is less than or equal to A, is less than or equal to B, is less than or equal to B prime, is also less than or equal to A, is less than or equal to B prime. So like this chain of, oh yeah, nice. This chain of conditions actually shows every possible equality that we could want. A is less than or equal to B is less than or equal to B prime. A prime is less than or equal to B is less than or equal to B prime. And A is less than, yeah, nice. So yeah, it is well defined. So, okay. So it's well defined. So from here, we know, first of all, reflexivity by just like choosing the equivalence class A, right? We know transitivity by just like picking elements. So if A is less than or equal to B and B is less than or equal to C, less than or equal to C, we have that A is less than or equal to C. Yeah, and then obviously the transitivity holds, and then from here the only thing else to show is that suppose A is less than or equal to B, and B is less than or equal to A. Less than or equal to A. Then we have that A is less than or equal to B, is less than or, and then B prime is less than or equal to A prime, with A less than or equal to A prime, and B less than or equal to B prime. So we then have that A is less than or equal to B, is less than or equal to B prime, is less than or equal to A prime, is less than or equal to A. So we have A is less than or equal to B prime. Yeah, that. Which implies that from this chain of conditions, that A is less than or equal to B, and B is less than or equal to A. Because we can just do this chain of conditions one more time, which shows that these are actually in the same equivalence class, so they're the same under the equivalence relation. Okay. And then the one thing to show is that in this case, we have the poset on n given by division is equal to z mod sim given by division. So what we do is, is isomorphic. So we just set an isomorphism that sends the equivalence class given by n to the absolute value of n. And it should be noticed that the absolute value of n is the n multiplied by a unit, so it's obvious that this just holds. And because of the unit, we can always go to the positive case, so yeah. Man, that's nice, okay. Yeah, that's okay. That's way more than I expected to prove with that. Because that is like just an entirely general construction. If you are associated with metric spaces, it's kind of, for some reason, it's gonna be reminiscent vibes if you take something which doesn't have the structure of equality at 0, and you basically say, okay, everything that has 0 distance is equal. We define them to be the same point. And this is the same thing lattice-wise. Like, if there's not, like, if they're equal both ways, then we define them to be the same thing. Alright, prove or disprove, z is opposed to that. This is false on its own. Draw the switching circuit. Okay. So draw a switching circuit for each of the following Boolean expressions. So A join B join A prime is the circuit that I'll draw one of these. And this is actually a 3-way parallel circuit. Alright, and then we have meet A. So we have meet that. And we have A, B, A prime, A. Now the thing to note about this example is that because A join A prime is equal to our maximal identity, this circuit actually just reduces down to just A. Okay. Alright, that will be close, exactly one of the 3. Oh gosh, let X be. This is previously proved, but you can do it by element-wise induction. I wonder what the formal proof of it is. I guess one way to do it is to basically show that letting x be equal to xn be the set of just arbitrary elements that we just label 1 up to n. We have that the cardinality of p of xn plus 1 but we can say pxn plus 1 is equal to pxn plus pxn plus pxn, the cardinality of that is cardinality of both of those. Cardinality of pxn union n plus 1, which this represents n plus 1 being added to every element of that. Oh gosh. Horrible spacing. There we go. Which is equal to 2 to the n plus 2 to the n. So we have 2 to the n times 2 equals 2 to the n plus 1. And then obviously it's the case for n equals 0, because in n equals 0, we just have the empty set. And n equals 1, you could also say we just have the empty set in 1. So you can use either of those as the base of the induction. Alright, each of the following I'm lazy. Okay, prove or disprove the set of non-zero integers is a lattice. I'm pretty sure the answer in this case would be no. And that's because you have your lower and upper bounds, but they can differ by a negative. They can differ by an associate. Or they can differ by a unit in other terms. And because they're like in non-zero integers has like multiple units, that fails. Alright, so okay, should at least upper bound in case so regenerate by that. Oh man. Give me a second. I'm not really interested in this. Not really feeling this. Not really feeling these identities either. Oh god. What baby a Boolean? Dog's barking at something. A totally ordered set. State of a B, total order. Or totally ordered sets beyond the usual ordering. Alright, so let x and y be posetsets. A map phi from x to y is order preserving. If a less than or equal to b implies that phi of a. If is that order preserving, which is not the case that every order preserving homomorphism is a lattice homomorphism. Okay. So if a is less than or equal to b, then we have that a meet b is equal to a. So phi of a meet phi of b is equal to phi of a, which implies that phi of a is less than or equal to phi of b. Oh, the dog is having a moment in the other room. Let me check that everything is good. Give me a second. Dog was having a crazy dream out there. Alright. Let B be a Boolean algebra. Not feeling this. Let B be a Boolean algebra. I mean, a lot of this is basic computations, and the thing that kind of sucks is I know this won't be mentioned in the rest of the book, so it's part of why I have kind of like little motivation for it. I kind of just like left off on that kind of like big note of, oh hey, lattice isomorphism to a Boolean algebra implies that it's a Boolean algebra, which shows that the division stuff that we've been working with does have inherently a Boolean algebra structure if we have no repeated indices. If we have, I wonder, okay. So suppose we have a repeated indice, right? Like a one-time repeated indice. So like let's take 2, 3 down 2 times 2. So like let's take 12. So 2, 2. So we have 4. 4, 6, 2 times 2 is 4, 12. So we have 1, 2, 3, 4, 5. I'm wondering if there's something about the amount of repeated indices you'd have to actually have in order to do it. So let's think. So if we have repeated indices, let's just consider in the case 1. So like we have P1, alright, so if you have factorization into not necessarily unique primes, P2, P1, P2, P3, all the way to P sub n, we're going to basically have the amount of elements in our lattice. So we have our lattice that. The order of the lattice is going to be, oh, there's a bird outside. Okay, sorry, I was distracted. So we're going to have the one element. plus we're going to have the amount of elements. We have 1 plus n plus the amount of ways there are to choose. Oh, so we have functionally the way we can choose 0 elements plus the way we can choose 1 element plus the way we can choose 2 elements, n over 2, and we can add on and on, which means that the order of the lattice is going to be equal to okay. There is some subtlety here. This is for the, oh, actually, by the way, this is, oh wow. Is this actually a really nice way to prove like one of the most famous identities? That it's something like the sum from I equals 0 to n of n sub I is equal to 2 to the n or something like that. Because this looks like a nice way to actually prove it. Because of the bijection. Oh god, I've seen one proof of this with graph theory and another proof now with lattice theory. This is insane. Okay. But you have some of these terms removed. You have some of these terms removed. So I'm wondering if you have any repeated indice, if it won't be isomorphic. I don't know. Oh gosh, I'll worry about that later. Alright. Yeah, Boolean switching function and variables. Write a program to divide Boolean variables. I'm not a programmer by trade, so. Yeah, if we have vector spaces next, oh my god, we're on chapter 20. That just hit me. Okay. Oh my gosh. But vector spaces and then module theory afterwards, I hope it gives us a little bit of an introduction to it. Because that's like a big thing in commutative algebra. I'm now reading that, like, the more I'm reading, the more I'm like, yeah, I'm definitely going to have to go over commutative algebra or commutative ring theory by Hideki Matsumura again. And then probably like Hearthstone for algebraic geometry. So, oh my gosh, yeah. I guess I'll just leave it off giving this page for the suggested readings and just writing my normal outro. Thanks for tuning in. Have a nice